All right, so here's another definition. A vector field is called conservative right? If it's the gradient of something. Cool with this? That would be like thinking about our usual capital F vector field, right? Happens to be the gradient of some function f. You guys cool with that? This should feel a little bit like the vector field f has an antiderivative.
Huh.
You guys remember that?
Okay.
Okay, so that's cool. It also turns out that there's this other thing. I'm probably spelling fundamental wrong. Fundamental. Fundamental? Oh.
That's good enough.
Whatever.
Yeah, that's it.
Fundamental theorem of line integrals.
Peculiar.
Okay. Do you all remember the fundamental theorem of calculus? Part 1.
Part 1.
Part 1. What does part 1 say? You guys use it all the time. We've used it like 6 times today.
It's reevaluated.
Okay, how about this? The integral from a to b.
Yeah, I'll take the word.
Maybe let me call this the integral over c, right? Because I'm doing a path integral. So the integral over a path of f dotted with dr is, well, so if f wasn't a vector field, if it was just some function, and you were integrating from a to b, what would you do? You do f of b minus f of a, where f is the antiderivative, right? Huh, cool. You can do the same thing here.
And those are scalar
So,
fs, right?
yeah, so I need the categories of this thing to make sense, so I have to think about this a little bit. Capital F's a vector field. Where the heck did little f come from? It should be playing the role of an antiderivative, right?
Yeah. It's the function.
From there.
So I need f to be the gradient of something for this to even start to make sense.
Okay.
You guys see that?
Yeah.
So this is true, but really only if gradient of that little function f is that capital F vector field. You guys see that? So if you can find an antiderivative, your life can be really easy because you just evaluate the function at the beginning of the path and the end of the path and subtract in the appropriate order.
And it might be as simple as like 3x plus 2y.
Yeah, right? If you can make this function that is, or that has this vector field as a gradient, this is going to be really, really easy because you don't have to parameterize the path. You don't have to deal with r prime. You don't have to dot product any damn thing, right? You just like find this antiderivative and evaluate. That's cool, that? That said, not every vector field has this property, right? So don't count on this sucker, right? You guys see that?
Yep.
Okay, there is a nice consequence of this thing, which is what?
Conservative functions.
So a little corollary. Conservative vector fields are, if it doesn't matter what the parameterization is, if it's only about the end, it's only about the beginning,
Oh, they're
they're
path independent.
path independent. You guys see that? So conservative vector fields are always path independent. The opposite is not necessarily true. So path independence does not guarantee conservative, but conservative guarantees path independence. Because you can just apply the fundamental theorem of line integrals. You guys cool with this?
Mhm.
The proof for the fundamental theorem of line integrals looks a little bit like the proof for the fundamental theorem part 1.
Okay.
You just kind of supply the idea of an antiderivative and crank on it. You guys cool with that? Okay, all right. So you should be able to do the 18.3 stuff, which is fundamental theorem of line integrals.